There's a dark beast sitting at the center of our galaxy that bends light, controls the orbits of millions of stars, and has never for once been seen directly. For 30 years, we called it a black hole and moved on. But a new study, published in February 2026, just put that assumption on trial, and the verdict isn't as simple as we thought. What if the dark beast at the heart of the Milky Way isn't a black hole at all? What if it's made of dark matter, the same invisible substance that holds entire galaxies together? And what if proving that would solve two of the biggest mysteries in physics at once? Stay tuned as we uncover the mystery of Sagittarius A. Let's start at the center, literally. 26,000 light-years from Earth sits Sagittarius A star, a compact object wrapped in so much gas and dust that we are unable to photograph it directly. We only know it's there because of the impact it has on its surrounding. The first hint came in 1933, when physicist Carl Jansky picked up a strange radio hiss coming from the constellation Sagittarius. He had no idea what it was. Neither did anyone else for the next 4 decades. It wasn't until 1974 that astronomers Bruce Ballack and Robert Brown isolated it as a single compact radio source. Brown later named it Sagittarius A star. For years, Sagittarius A stayed a mystery. And then, in the 1990s, telescopes got sharp enough to track individual stars looping around what looked like empty space, at speeds that made no sense. One star, named S2, completes a full orbit in under 16 years. Our Sun takes 225 million years to go around the Milky Way galaxy. Something at the center was throwing S2 around like a slingshot, and whatever it was had to be millions of times heavier than the Sun, packed into a space smaller than our solar system. In 2020, the Nobel Prize in Physics went to Reinhard Genzel and Andrea Ghez for nailing down the numbers. 4.3 million solar masses, crammed into a region you could fit inside the orbit of Mercury. Roger Penrose shared that same prize for proving, mathematically, that black holes are an unavoidable consequence of Einstein's equations. Case closed, right? Not quite. Read the actual Nobel citation and it says, supermassive compact object, not black hole. That distinction has just become a lot more important. Here's the problem nobody likes to talk about. We don't actually know how objects like Sagittarius A star are born. Smaller black holes, the ones a few times to a few 100,000 times the mass of the Sun, form when massive stars run out of fuel and collapse. We understand that process well. We've watched it happen. But there is no star massive enough, no known process violent enough, to directly collapse into something 4.3 million solar masses. Supermassive black holes are common across the universe, and we still don't have a clean explanation for how the first ones got so big so fast. That gap in our knowledge is exactly where a new idea has been quietly growing for over 50 years. In February 2026, a team led by Dr. Valentina Crespi at the Institute of Astrophysics La Plata in Argentina, working with physicist Carlos Argüelles, published a paper in the monthly notices of the Royal Astronomical Society that ran a direct comparison. On one side, the standard black hole model. On the other, a dense core made entirely of dark matter. They tested both models against the real orbital data of S2 and 5 mysterious objects called G sources, gas cloud-like bodies that stretch and deform as gravity drags them past the galactic center. The result? The dark matter model matched the orbits just as well as the black hole model. Statistically, you cannot currently tell the two apart. So what is this dark matter supposed to be made of? This is where it gets genuinely strange. The team's model uses something called fermionic dark matter, an idea first proposed back in 1969 by physicists Remo Ruffini and Silvano Bonazola, decades before anyone had the data to test it. Fermions are a known class of particle. Electrons and quarks are fermions. They all obey a rule called the Pauli exclusion principle, which says no two identical fermions can occupy the exact same state at the same time. It's the reason atoms take up space, the reason your hand doesn't pass through a table. The proposed dark matter fermions would follow that same rule. They can't be crushed infinitely small. Squeeze enough of them together and they push back, building up immense internal pressure, enough, in theory, to support an object with the mass of millions of suns without ever collapsing into a singularity. No event horizon, no point of no return, just an extraordinarily dense, stable ball of particles that happens to weigh as much as a small galaxy's worth of stars. And the model doesn't stop at the core. The same fermions are predicted to thin out into a vast, diffuse halo stretching across the entire galaxy, which means, in this theory, Sagittarius A star and the dark matter halo wrapping the Milky Way aren't two separate things. They're one continuous structure. No other model on the table connects the galactic core to the galaxy-spanning dark matter halo like this one does. That detail matters more than it sounds, because dark matter itself is one of science's oldest unsolved cases. Back in the 1930s, astronomer Fritz Zwicky noticed galaxies in the Coma cluster moving so fast they should have torn themselves apart. Something invisible had to be holding them together. Decades later, galaxy rotation curves showed the same thing, outer stars orbiting faster than visible matter could explain. Today, we estimate dark matter makes up roughly 85% of all matter in the universe, and we still don't know what a single particle of it actually is. This is where the Crespi model pulls double duty. If the core of our galaxy really is fermionic dark matter, it doesn't just replace a black hole. It hands us a leading candidate for what dark matter is, backed by the one place in the universe where we can actually test it. There's more supporting evidence, and it comes from an unexpected source: Europe's Gaia spacecraft, which has spent years mapping the precise motion of over 1 billion stars. In 2022, Gaia's data revealed something odd happening at the outer edge of the galaxy, a sharp drop-off in rotation speed known as a Keplerian decline. Most dark matter models struggle to explain that cutoff cleanly, but a fermionic halo, limited by that same exclusion principle, naturally produces a sharper edge than other dark matter candidates, which lines up with exactly what Gaia saw. Then there's the elephant in the room, the actual photograph. In 2022, the Event Horizon Telescope released its iconic image of Sagittarius A star, a dark shadow ringed by glowing light, hailed worldwide as a picture of a black hole. But a 2024 study by researcher Joaquin Pele and colleagues showed something unsettling. A dense, fermionic dark matter core would bend light just as powerfully, producing a shadow and ring image that current telescopes cannot distinguish from the real thing. The photo doesn't settle the debate. It's compatible with both answers. If the dark matter model holds up, it could also explain something else that has puzzled astronomers since the James Webb Space Telescope came online: little red dots. These are compact, impossibly massive objects glimpsed in galaxies from less than 1 billion years after the Big Bang. Far too early, by conventional thinking, for a black hole that size to have formed. A fermionic dark matter core doesn't have that problem. In the dense early universe, these particles could clump directly into massive cores without needing a dying star to start the process at all. Now, before this runs away into science fiction, Crespi and her team are explicit that this is not proof. The black hole explanation still has the overwhelming weight of evidence and consensus behind it. What this paper does is something more careful and arguably more interesting. It shows the alternative cannot be ruled out, and that it deserves serious testing. So how do we actually settle this? There's one signature a black hole has that a dark matter core never could: a photon ring, caused by light looping repeatedly around the event horizon before vanishing. A stable dark matter core has no horizon for light to fall into, so no true photon ring should ever form around it. Spotting or ruling out that ring is the next major target. The Gravity Interferometer in Chile is already tracking tiny shifts in S2's orbit with extraordinary precision. And future instruments, including proposed next-generation space telescopes working with the Event Horizon Telescope network, may finally get the resolution needed to check. Meanwhile, on Earth, dark matter detectors are hunting for direct evidence of these particles in laboratories, searching for the faint fingerprints fermionic dark matter should leave behind if it's really out there. What makes this story worth following isn't that black holes might not exist. They almost certainly do, somewhere in the universe. It's that the thing sitting at the very center of our own galaxy, the anchor every star, including our sun, has been orbiting for over 4 billion years, might still be something we haven't correctly identified. And if it turns out to be made of dark matter, we won't just have rewritten the story of the Milky Way's core. We'll have found, hiding in plain sight the whole time, the answer to what most of the universe is actually made of. We've stared at the heart of our own galaxy for a century, and we still aren't sure what's staring back. That should tell you something about how much of the universe is still left to discover, and that's exactly why this channel exists. If you want to keep exploring questions like this one, subscribe and join us for what's next.